This is the enolate chapter, slides 15 to 20. So again, we're still talking about enolates. The only difference I'm going to show you now in the 1,2 addition is that instead of reacting the enolate with another aldehyde or ketone as a 1,2 addition, let's use an enolate and interact with a carbonyl that has a good leaving group off of it. This reaction specifically is called the Claisen condensation, but you know me, I'm not too concerned about the names. I really want to make sure that you understand the mechanism. So let's take this methoxy ester. We can react it with a base just like we did for the formation of an enolate using a ketone or an aldehyde. Now notice that despite this being an asymmetric carbonyl, there's only one alpha carbon. So the other side is an oxygen. So therefore, I'm not going to be deprotonating a proton off of the oxygen because it's an ester. So there's really only one side. I don't have to worry about kinetic versus thermodynamic enolates. So I can use something like sodium methoxide. All right, so here's my alpha carbon. There is an alpha hydrogen. I'm going to start with my acid-base chemistry and deprotonate, forming my enolate. Okay, now I'm going to interact. If you look at step 1B, so this first step was acid-base chemistry. Step 1B is introduce a carbonyl. So we're actually going to do it on the same molecule. So another molecule of itself is floating around. And remember, the alpha carbon is the nucleophile. The enolate collapses down, and the pi bond attacks the carbon of the carbonyl in a 1,2 addition. Let's number our atoms. 1, 2, 3, 4. Okay, now what we have is carbon 3, which still has the O methyl off of it, is now got an oxygen and a negative charge. It still has carbon 4 off of it. Just going to put carbon 4 over here. Carbon 3 has been attacked by carbon 2. Carbon 2 is still attached to carbon 1. Carbon 1 now has the double bond oxygen back, and carbon 1 also has an oxygen methyl off of it. Carbon 2 was the one that did the attacking. So we did our in-up reaction. In-up. But now, because we attacked an ester and not a ketone or an aldehyde, we have to consider the down-out. And in this case, because there is, off of carbon 3, there is a group that is not a carbon or a hydrogen, we can do down and out. It's like we're driving the blue group on, we're driving the yellow group off. Right? So we're kind of combining our chapters now. Four, 3, 2, and 1. We have just made a 1,3 dicarbonyl system. So let's examine driving these reactions towards these products. Notice the equilibrium arrows I have at the top. Notice that the beta dicarbonyl, right? So any one of these systems, you could have a keto-keto, you could have a keto ester, you could have an acid-acid, but they all have a 1,3 relationship. The carbonyls are 1,3 apart. These are really special systems. So when you can create these 1,3 carbonyl systems, This allows you to do so much more. So let's take a look at a diketone system. Look at A. Let's talk about the pKa's of each one of these. The pKa of A is just a regular alpha carbon bearing a proton. And I already told you that the pKa is roughly 19. The pKa of B is much, much lower. It's more around, depending upon the carbonyl system, you could say it's around 9, 10, 11, somewhere around there. It just really depends on the carbonyl system. That is a huge increase in acidity, because remember, water pKa is 15.7. So you went from worse than water to way better than water. Can we figure out, using what we know, why this would be the case? Why is B far more acidic than A? You can use Ario. If we remove one of the protons, acid-base chemistry, we want to analyze the negative charge left behind. Versus right, so if I remove the proton on one side versus another, how does Ario help us to understand the stability of either of these? You start with A, the atom. Well, they're both carbons. Carbon versus carbon. So that's not helping us. How about R, resonance? If you look at resonance for the first system, you can see that resonance is actually across 1, 2, 3, 4, 5 atoms. You can resonate that negative charge in either direction, up towards either of the oxygens. So that negative charge is distributed across 5 atoms. So you could say negative charge delocalized across, this one is 5 atoms, and the one on the bottom is just 3. So the more atoms that you delocalize the charge over, the more stabilized it is. If the negative charge is more stable, then it's more likely to give away a proton. If it's more likely to give away a proton, it is a better acid. So this increased acidity is what drives the Claisen condensation equilibrium. And so we can end up having our 1,3 dicarbonyl systems made very efficiently. Notice the base I chose to use. Typically in these reactions, since we're not worried about kinetic versus thermodynamic, we tend to use the thermodynamic type bases. On top of that, in order to avoid nucleophilic reactions, well, we're not really avoiding them, but if they are occurring, we're not seeing them. Here's why. Notice that I try and match the ester to the type of and to the type of base that I'm using. So if I were to use sodium ethoxide, and by chance it does a derivatization product in up, if it comes down out, So if I'm driving this on and driving the other one off, notice that I end up at the same starting material. So even though I'm adding sodium methoxide, so even though we saw in the last chapter that these can do a trans-esterification in up, down, out, we're not saying it's not happening. We're not saying that this isn't in competition. But if it is, you're only just getting more starting material, right? And you're never going to see the result of the trans-esterifying it with itself is just going to give you more starting material. So ultimately, this will act as a base so that you can do these reactions. Same goes for the methoxy. So you'll notice that I try to design the base to look like the ester so that if this in up, down, out exchange is occurring and competing with going after the alpha position proton, I'm not seeing the result of it because it's just going to keep giving me back my starting material, which ultimately will do the chemistry I want to do because the chemistry that I want to do will yield something different. So that's why you see us toggle between sodium methoxide and sodium methoxide. Take a look at the ester that we're using. You'll see the trend. I'll leave this one for you guys to do as a practice. Notice that you change one little thing and everyone gets their name on it. So in this case, if you do the same type of reaction, but intramolecularly, it's a named reaction called the Decarboxylation condensation. So I'll have you guys work on this reaction. It's just the same as what we just did, except it's intramolecular. All right, so what can we do with these 1,3 dicarbonyl systems? And as it turns out, we're able to leverage the acidity of that proton to help us when we don't get really good regioselective results when we're trying to design the synthesis of a compound. So here's a challenge. Let's say we had a starting material shown here. Here's a starting material. And if you'll notice, it's asymmetric. There's an ethyl on one side and a methyl on the other. And the desired product we want is to form an enolate, a thermodynamic enolate, right? Because we want it on the more substituted side. And we want to add this benzyl system. And we would really like to avoid forming the benzyl alkylation on the kinetic side. So we want thermodynamic product only. The problem is that the starting material we're using, I know it's asymmetric and I know technically one side would give a thermodynamic result, but the kinetic product versus the thermodynamic product, it's not like a huge steric hindrance issue. So going after the secondary one versus the primary one on such a small molecule is not going to yield 99-to-1, thermo to kinetic results. So how can we improve, maybe even get 100% regioselectivity of the thermo product and avoid making any of the kinetic product? This is just to show you how we can go about doing this. And what we're going to do is exploit our use of the 1,3 dicarbonyl. So the first thing we're going to do is add some base, and I'm going to use the methoxy because that's what my ester looks like. And then once I have made my enolate through acid-base chemistry, it's going to react with itself. So acid-base chemistry, the alpha hydrogen gets removed to form the enolate. The enolate collapses and does a 1,2 addition. We're driving the carbon on. We're driving the methoxy off. Let's number 1, 2, 3, 4. 1, 2, 3, 4. I have not kicked off that group yet, but I can come down and out. So we did in, up, down, out. Okay. Now we have a 1,3 dicarbonyl system. Okay, so this part right here is this part right here. So what do we have? Oh, and this. So what do we have? We have, we'll call it carbon 5 and carbon 6. So I need to add at that position that's most acidic a methyl group and a benzyl group. So what I'm going to do is I'm going to do a very simple, if I add one equivalent now of sodium methoxide, the best and most acidic, no competition. We're not talking about a competition, right? Because I want to point out up here, let me write this out. If I had a ketone, even if I had this asymmetric ketone, the pKa of each of the protons is about 19. Trying to get the thermodynamic versus kinetic enolate was all based on steric hindrance and stability of the enolate. It had nothing to do with trying to use a base that was only going to go after one versus the other. The bases we chose had everything to do about steric hindrance and equilibrium, not about their ability to deprotonate one versus another. The bases we've chosen for these types of kinetic versus thermodynamic systems, they are strong enough to deprotonate either one because the pKa for either one is about the same. Once you make it a dicarbonyl, however, the pKa is now about 9. Now it's not a competition. This isn't about steric hindrance anymore. This is like the pKa of the proton is 9 or 19. Well, which, if you had one equivalent of base, which one's it going to go after? It's going to go after the most acidic one. So we're going to do acid-base chemistry. And then you're going to add an alkyl halide so that you can do an SN2. Oof, look at that. Oops. We are so close. We have now made, we've put carbon 5 on. Understand we still have one more proton that has a really good acidity. So I'm going to continue on the next page. Actually, let's hold off. I'm going to also put on carbon. I've run out of space. I sorely underestimated how much space I would need here. Sorry, guys. But the next step is to add another equivalent to remove the next one and introduce an alkyl bromide. So I want to do another acid-base reaction and another SN2. So I'll pick up from here on the next slide. Let's write this down at the bottom. So So if I added another equivalent of sodium methoxide, I would do an acid-base reaction, form the enolate. I'll just write it as a carbon minus. Add the benzyl bromide, primary carbon, and I'm going to do an SN2. Now, if you look, that is the molecule we want, right? So our goal from the previous slide was to make that. And if you look, that is our goal in green. So here's the problem. We need to get rid of this ester group hanging off, okay? How do we do that? Well, we can do that through a reaction called decarboxylation. So I'm going to show you this new reaction. It's an intramolecular acid-base reaction. And the only time you can do it, look at, all you need is heat. But the only time you can do it is if you have a 1,3-dicarbonyl, and, so these are your needs, you need a 1,3-dicarbonyl for this reaction to work, and you need 1 carbonyl, has to be a carboxylic acid. All right, if you have that, you can heat this up and drive off carbon dioxide. How does that work? I'm going to redraw this exact system. There's carbon 1, carbon 2, and what I'm going to do is I'm just going to rotate around the 2, 3. So here's carbon 3. But instead of going up with the carbonyl, I'm going to draw what really is occurring. I just rotated it. This is a more accurate representation of how this molecule sits. Why? Because you have intramolecular hydrogen bonding there. You have the partially negative carbonyl oxygen and the partially positive protic hydrogen from the carboxylic acid. So that is intramolecular hydrogen bonding, and look at it, it's forming a perfect 6-membered ring, which we know is it's a pretty nice sized ring for stability. So with just a little bit of heat, the pi bond of the carbonyl makes a real bond between the oxygen and the hydrogen. And as that bond forms, the oxygen-hydrogen bond collapses. And as that bond forms, the carbon 2,3 bond collapses. It's like a cyclic, it's a concerted mechanism, and it thus gives us, let's see what happens arrow-wise with heat. We have OH, double bond, C, double bond O, that's carbon 3, carbon 1, and carbon 2. So if you notice, carbon 3, actually I'm going to write it down here. Carbon 3 is carbon dioxide. So we have lost carbon dioxide as a gas. It bubbles away. What we're left with is an enol. So now that we have the enol, we need to tautomerize it. Because enols are not stable. So after it collapses intramolecularly and the carbon dioxide goes away, the enol tautomerizes and you're left with the carbonyl. All right, let's put it all together, guys. Now we can finish the reaction. You can see up in the top hand corner, I have a reminder as to what the desired product is. This is where we left off on the previous page. We are so close to having the final product in hand. And with no competition, we didn't have to worry about kinetic versus thermodynamic competition. So from here, all we have to do, we have the 1,3-dicarbonyl. Our only issue is that we don't have the carboxylic acid. So all we have to do is do a saponification. So we're going to do our 1,2 addition, changing our ester in and up from last chapter. We're driving the OH on. We're driving the methoxy group off. Now we can do our down and out. We now have our 1,3-dicarbonyl, and you can see that we're set up now for the carbon dioxide to be expelled. So we can redraw this. Redrawn. Concerted intramolecular acid-base reaction, arrow push. Gives us CO2 gas and our enol, which I should probably do better arrows, tautomerizes to the final product. Ugh, this one's ugly. Sorry about that. There. So you can kind of see where this is going. Try to highlight the path here so you can see that really what we were doing is we were using the 1,3-dicarbonyl ultimately. We were using it simply to get the infrastructure we wanted without competition, knowing that the other carbonyl would be able to be erased, if you will, through decarboxylation after we were done adding everything we wanted to at the alpha position. So we got to do 2 alpha alkylations without worry about competition, and then just simply get rid of the ester through changing it to a carboxylic acid through decarboxylation. Ugh, I know, that's kind of like long and you know, lengthy and steppy, but at least it works and we have lots of different options. People probably would avoid this if your carbonyl in the beginning had a little bit more asymmetry with, steric bulk. So let's say you were going after the alpha carbon shown on the right versus on the left. You might get better thermodynamic kinetic control for that molecule, but for a small guy, not so easy.